Now, finally, for today, I have one more section to start with. I probably will not finish it. I want to show you now one or two things because that is needed to answer some of the questions which are already in the next practice examples. Chapter 3.5 was about stress equilibrium. Chapter 3.4 was about transformation of stress. Chapter 3.3 was about eigenvalues of stress. Now, the eigenvalue of stress, there we were asking, you remember, we were asking, is it possible to put the stress vector on a cut, on a surface, such that it's parallel to the normal vector? And that gives you the definition of the procedure for eigenvalue calculation. That gives you the definition of the maximum normal stresses, actually. Now, if you ask the question slightly differently, is it possible to place the cut such that the vector P is perpendicular to the normal direction? Okay, then you will get actually the definition of maximum shear stress. I will not go through in too much detail through these calculations, but I want to show you quickly how to do it. It's the same philosophy. You ask for the maximum normal stresses. Now we ask for the maximum shear stresses here. Okay, now, since the eigenvalue stress is so much shorter, so much nicer, it has the many zeros, we use that one now to begin with. So if we have the eigenvalues of stress, then we can work and try to find a position where the P vector is parallel to tau, to the shear stresses, and thus perpendicular to n. Okay, so apply an arbitrary oriented surface with normal vector n and use the Cauchy formula. Now this section 3.6 is now bringing together all the previous section from 3.1 to 3.5. Sigma h is the vector in its eigensystem, n is the normal vector on the cut, and p is the stress vector, which corresponds to this combination here. So p is that what we search, and we want to have p perpendicular to n, and let's see what that gets. In the previous case, we had p parallel to n, and that gave us the eigenvalues. Okay, magnitude of sigma, normal stress on the surface. Insert all the definitions which we have calculated and used before. I really don't want to go through all these details. And use Pythagoras, right-angled decomposition of the stress into its normal stress and into its shear stress. So this is the total stress. This is the normal stress corresponding to eigenvalues. So when I take Pythagoras, I subtract the normal stresses from the total stress, I get this shear stresses, and everything is squared in Pythagoras. Okay, now when you follow this calculation, you can go through this slowly until next time if you want. Then you find an equation for tau squared, and the extrema of such an equation, the extreme values of such equation, those you find by taking the first derivative with respect to the unknown n, which is the direction. So which direction is this? We want to know, and tau square, if the derivative is 0, then we know we have mathematically identified a maximum and extremum, a maximum or a minimum actually. Okay, again, a lot of repetition of mathematics. These are the steps how to do it, and you will get, you will get one solution which corresponds to n1 equals 0. First solution corresponds to tau equals 0, which is actually not the interesting one. We want to have either positive or negative values, and the second solution gives you something which looks like tau equals sigma 2 minus sigma 3, tau equals sigma 1 minus sigma 2, tau equals sigma 1 minus sigma 3. These are the difference, all the three possible differences between eigenvalues. And this is coming from the solution to the extremes. Okay, maximum shear stress, sigma 1 minus sigma 3. And now this one we can choose from those three only after we have sorted the eigenvalues. If sigma 1 is the maximum eigenvalue, sigma 3 is the minimum eigenvalue, then we know sigma 1 minus sigma 3 is always the largest possibility from those three. Shear stress maximum is the red equation. So this is a standard 1 to 2 point question in our exams. And actually this one corresponds to a 45 rotation around the 2 axis, which we were talking about. Okay, this one, I stop here. I will show you this one next time. Okay, so that it corresponds to exactly 45 degrees, I will show you next time. This one will also allow us to build a rotation matrix, which I don't have enough time today. In the next 5 minutes, that will take a little bit longer. So next time I will show you again how to build a rotation matrix. Next time I will show you how to use it and how to identify what is the angle between the eigensystem and the maximum shear stress eigensystem.